Ice giants, the cool cousins. Speaking of cool, let's talk about the ice giants, Uranus and Neptune, as mentioned before. These giants have a higher proportion of elements like oxygen, carbon, and nitrogen locked away as ice within their interiors. They're still pretty hefty, but with a slightly different chemical makeup. These frigid giants are like cosmic freezers, holding clues to the information of our solar system and potentially harboring exotic oceans of liquid beneath their atmospheres. Dwarf planets, the underdogs with bite. Not all celestial A-listers make the planetary cut. Enter the dwarf planets like Pluto and Eris. These feisty underdogs, rounded and gravitationally dominant, haven't quite cleared their cosmic neighborhood. Think of them as the plucky contenders in the planetary world, packing a punch but missing the Premier League. Pluto, the dethroned ninth planet, don't feel sorry, boasts a heart-shaped ice plain, a thin atmosphere, and intriguing moons. Eris, another contender, might be bigger than Pluto, but its distant icy orbit makes it a frosty proposition for any visitor. Carbon planets, diamonds in the rough. Literally. The universe loves throwing us curveballs, and carbon planets are a prime example. These theoretical worlds are thought to have surfaces laced with graphite or even diamond. Imagine a giant disco ball planet. The intense heat and pressure on these planets could have cooked up all the carbon into these exotic forms. These planets might not be ideal for life, but they show wild ways planets can form. Maybe they're leftovers from old stars or wreckage from cosmic crashes. Ice planets, snowballs with secrets. Brr! Time to trade heat for ice cubes. Enter the ice planets. These frozen giants are cosmic snowballs, with surfaces of water ice, methane, and ammonia. Imagine a giant comet, but way too big for a slingshot. These frigid giants might hold the key to our solar system's birth. Since it all started as a dusty cloud, ice giants likely formed in the chilly outer areas. Studying their makeup can help us picture the conditions back then. Who knows? These icy worlds might even hide secret oceans under their frozen exteriors, maybe with life that loves the cold. That'd be a truly icy discovery. Desert planets. A parched paradise. Not. All right, feeling parched? Skip the desert planets. These desolate worlds are sun-scorched, with no air and scorching temperatures. Imagine Tatooine from Star Wars, but way hotter and rockier. Not a vacation spot. Brutal sun rays would zap any water, leaving a barren wasteland. But hey, even these tough planets have value. Studying their geology reveals how intense radiation shapes planets, helping us understand how rocky planets form and evolve in general. Rogue planets, nomads of the cosmos. Space can be a lonely place, and some planets reflect that to become the lonely hearts of the cosmos. Meet rogue planets, cosmic nomads with wanderlust. These giant balls of rock and ice drift through the darkness unattached to any star. Imagine a giant snowball on a never-ending road trip. How'd they get there? One theory, they were kicked out of their star systems during giant space brawls. Another idea, they never got hot enough to become stars in the first place. Studying these rogue planets could unlock secrets about how planets form and the crazy dynamics of star systems. Substellar objects, brown dwarfs, blurring the lines. Space throws some shade sometimes. Brown dwarfs are like failed celebrities. They just don't have what it takes to be a star. Too big to be a planet, not big enough to ignite their core, they're stuck in a cosmic no man's land. Imagine a dim bulb trying to be a sun. That's a brown dwarf. They might be faint, but studying these cosmic wannabes can teach us how stars form and what makes them tick. Or not tick in this case. Mini Neptunes. The missing link. Cosmic Curiosities Alert. Buckle up for Mini Neptunes. The pint-sized ice giants. Smaller than their big cousins, they pack a punch with thick, icy atmospheres. These weirdos might be the link between rocky super-Earths and full-blown ice giants. Imagine an ice giant that ditched the gym. That's a mini Neptune. Studying their makeup could reveal clues about how planets were formed way back then, helping us solve the cosmic puzzle. Gas dwarfs, the runts of the litter. Not all gas giants are equal. We have gas dwarfs, the runts of the litter when it comes to these giants of the cosmos. They're smaller than their big brothers like Jupiter and Saturn, but still pack a punch with their thick atmospheres, primarily composed of hydrogen and helium. Think of gas dwarfs as the mini-me's of the gas giant world. While they might not be as massive or awe-inspiring, they still offer valuable insights into planetary formation processes. Studying their composition and structure can help us understand how gas giants form and evolve, and how they differ from their larger counterparts. Chthonian planets, Inferno worlds. And here's another for the heat lovers. Chthonian planets, also known as Inferno planets, are basically giant balls of iron. Imagine a world so scorching it'd melt your spaceship on landing. Not exactly a vacation spot. These fiery planets are rumored to be the leftover cores of smashed-up celestial bodies, their iron hearts laid bare to space. The heat on these inferno worlds is so intense it would vaporize any atmosphere that dared to form. But hey, even these fiery friends have a story to tell. Studying their makeup could unlock secrets about the solar system's wild past, like how planets form cores and how cosmic crashes shape planetary evolution. Iron planets, a theoretical inferno. Speaking of iron, some theorists propose the existence of iron planets. These would be balls of solid iron, much denser than even Earth. While their existence remains unconfirmed, they paint a fascinating picture of planetary diversity. Imagine a planet where the ground beneath your feet is literally iron. Iron planets could form in extreme environments, perhaps from the remnants of exploded stars, or the cores of giant planets ripped apart by powerful gravitational forces. While they might not be hospitable to life as we know it, iron planets could offer valuable insights into the exotic possibilities of planetary formation under extreme conditions. Tatooine-like planets, double trouble suns. Remember Tatooine from Star Wars with its twin suns? Well, those are Tatooine-like planets orbiting binary star systems. These planets might experience dramatic swings in temperature depending on which star they're facing, creating a truly unique environment. Imagine a scorching day followed by a frigid night, all within a single planetary rotation. The presence of binary stars can also affect a planet's tides, potentially creating massive tidal bulges and influencing the planet's overall climate. Studying Tatooine-like planets can help us understand how stellar multiplicity impacts planetary formation and evolution. Circumbinary planets, a dance with two stars. But binary stars can even get more complex. We have circumbinary planets that actually orbit both stars in a binary system. Imagine a cosmic ballet with a planet gracefully waltzing around two suns, bathed in their combined light and warmth. The gravitational forces at play in a circumbinary system would be unlike anything we experience on Earth. Studying these planets can help us understand the complex orbital dynamics of multiple star systems and the potential challenges and opportunities for life in such environments. Habitable havens, the Holy Grail. Now let's talk about the Holy Grail of planetary science, habitable planets. These are worlds that could potentially support life as we know it. They need to be in the Goldilocks zone of their star system, not too hot and not too cold, and have a suitable atmosphere and liquid water. The search for habitable planets is a major focus of modern astronomy. We're constantly scanning the cosmos for exoplanets that might harbor the conditions necessary for life. Finding a truly habitable planet would be a revolutionary discovery, potentially answering the age-old question, are we alone in the universe? Super Jupiters, gaseous giants on steroids. Our exploration isn't over yet. We have super Jupiters, gas giants on steroids that dwarf even our mighty Jupiter. These behemoths can have masses several times greater, pushing the boundaries of what we thought possible for planets. Imagine a gas giant so massive it could swallow several Jupiters whole. Super Jupiters might form in very dense regions of stellar nurseries, where immense gravitational forces pull in vast quantities of gas and dust. Studying these colossal planets can help us understand the extremes of planetary formation and the factors that influence a planet's ultimate size and composition. Helium planets and beyond. The unknowns. You see, the universe loves surprises, and astronomers are constantly discovering new types of planets. We have theoretical helium planets, composed mostly of helium, the second most abundant element in the universe. Their existence is yet to be confirmed, but they paint a picture of truly alien worlds. Imagine a planet where the air you breathe, if you could breathe on a helium planet, is lighter than air on Earth. Helium planets could form under very specific conditions, perhaps from the remnants of exploded stars, or the outer layers of giant planets ripped apart by powerful stellar winds. While their existence remains theoretical, the possibility of helium planets expands our understanding of the diverse building blocks that can form planets. Silicate planets and beyond. The building blocks. Alright, most planets including Earth are composed primarily of silicate minerals. These are rock-forming compounds like silicon dioxide, quartz, and magnesium silicate. Understanding these silicate planets helps us piece together the formation of our own solar system and the early stages of planet building. Studying the composition of silicate planets can reveal clues about the conditions that existed in the protoplanetary disk, the swirling cloud of gas and dust from which our solar system was formed. By analyzing the types and ratios of silicate minerals found on different planets, we can start to understand how planets differentiate and evolve over time. Silicate iron planets and beyond. The melting pot. Many planets are a blend of different materials. Silicate iron planets are a prime example, combining silicate minerals with iron, forming the core composition of many rocky planets. Imagine Earth, but with a slightly different recipe. A bit more iron in the mix. The ratio of silicate materials to iron in a planet can influence its overall density, magnetic field strength, and potential for harboring life. Studying silicate iron planets can help us understand the internal structure and composition of different types of planets, providing valuable insights into planetary formation and evolution. Lava planets. Erupting and simmering surfaces. Ever imagine a planet that's basically a giant lava lamp? Buckle up because lava planets are totally a thing. These fiery worlds are like Earth, but turned up to 11. Their surfaces are constantly molten, a sea of liquid rock hotter than anything we can imagine. Volcanoes wouldn't even be a thing on a lava planet. The whole surface is already erupting. Scientists think these inferno worlds might be superhot planets that formed way too close to their star, or maybe even the result of supermassive collisions. Studying these molten messes could help us understand how planets evolve in these extreme environments, and who knows, maybe even how they cool down eventually. Eccentric planets and beyond. Orbital oddities. For your interest, let me tell you guys, not all planets follow circular orbits. Eccentric planets have highly elliptical orbits, taking them closer and farther from their star throughout their year. Imagine an Earth that experiences scorching summers and frigid winters on steroids, all due to its wonky orbit. The extreme seasonal variations on eccentric planets could pose challenges for habitability. However, they might also create unique niches where life could potentially thrive, perhaps in subsurface oceans shielded from the harsh extremes on the surface. Studying eccentric planets can help us understand the complex orbital dynamics of planetary systems and the potential impact of elliptical orbits on planetary environments. The classics revisited. Terrestrial planets. First up, the familiar faces from our own solar system. We have the terrestrial planets. Our celestial neighborhood brims with rocky planets. The cosmic brick and mortar. These Earth-like planets with their iron and silicon cravings are the solid citizens of our solar system, holding their own against the swirling gas giants. But within this group lies surprising diversity. Mercury, the Sun's pint-sized speed demon, zooms around in a record 88 Earth days, a scorched world with daytime temperatures that would melt lead. Venus, Earth's sizzling sister, boasts a crushing atmosphere choked with carbon dioxide, creating a runaway greenhouse effect that would make you sweat on the hottest summer day times a million. Earth, the undeniable jewel, is the only known life-harboring planet in our system. With its liquid oceans, breathable atmosphere, and ever-changing climate, it's a dynamic and fascinating world. And then there's Mars, the rusty red neighbor. With its thin atmosphere and freezing temperatures, it might not be your ideal vacation spot, but recent discoveries of water ice hint at a wetter, warmer past. Maybe Mars is the fixer-upper project of the planetary world waiting to be revealed. Gas giants, the swirling kings and queens. Time to step aside, brick houses. these gas giants are here to steal the show. These heavyweight champions rule the solar system with their massive swirling bodies of gas, mostly hydrogen and helium. They put on light shows that would outshine any disco ball with their colorful atmospheres. Jupiter, the king of these gas giants, is a swirling storm king with its iconic Great Red Spot, a monstrous hurricane raging for centuries big enough to swallow Earth whole. Saturn, the ringed wonder, boasts a dazzling system of ice dust particles, a constant source of awe for astronomers. Uranus and Neptune, the cool cousins, tilt on their sides like cosmic bowling pins. Their methane-laced atmosphere gives them a beautiful blue-green hue. They might not be flashy like Jupiter and Saturn, but they hold mysteries like Neptune's unexpectedly hot core. The exotic, hot Jupiters, super-Earths, and more. Our solar system is just a tiny bubble in the vast universe, and beyond it lies a treasure trove of exoplanets, planets orbiting stars other than our Sun. These alien worlds come in all shapes and sizes, pushing the boundaries of what we thought possible. Let's meet the hot Jupiters. Imagine a gas giant cranking up the heat. These scorching planets hug close to their stars, whipped by scorching winds and temperatures that could melt metal. Not exactly ideal for a vacation. In contrast, we have super-Earths. These rocky planets are Earth-sized or even bigger, but with a much denser composition. They might have thick atmospheres or even exotic surfaces, making them intriguing candidates for harboring life. We'll get to that later. Oceans galore. Ocean planets and water worlds. Calling all thirsty astronauts. Ocean planets might be your nightmare. Just think of it as a giant floating water droplet, swirling with currents. Sounds refreshing, right? Wrong. These cosmic oceans cover everything, with nary a drop suitable for drinking. The crushing pressure at the bottom is mind-blowing, and forget building a sandcastle, there's no solid land. But hey, for bizarre deep-sea creatures, these watery worlds could be a haven. Taking it a step further, we have water worlds that take things to an extreme. Imagine a giant ball of water, no land in sight, where you could dive forever. The pressure down there is mind-boggling, but some scientists dream of life forms thriving in this watery abyss. Microscopic organisms suspended in their water column, fueled by deep-sea vents instead of sunlight. That's the wild theory. Water worlds might harbor truly alien life, making them a goldmine for astrobiologists. Pulsar planets, idle drifters of the space. Ever heard of a zombie star? No, not like the shambling kind. Pulsar planets are basically planets orbiting dead stars, but these aren't your average deceased suns. These pulsars are super-dense neutron stars that spin super fast, like cosmic lighthouses, blasting beams of radiation. These pulsar planets are loners, just like their rogue cousins, but they formed in a different way. Maybe they were part of a double-star system where one star went supernova, leaving behind the super-spinning neutron star and the leftover planet in its wake. Studying these pulsar planets is like looking back in time, helping us understand how stars die and how planetary systems can survive such dramatic events. Let's turn to some speculative theories. Well, cloud planets. These are hypothetical planets with thick atmospheres that obscure their entire surface, making it impossible to see if they have a solid core or not. They might be hot and gassy like Jupiter, or cooler and shrouded in thick clouds of water vapor or methane. Then we have magnetar planets. These are even more theoretical than cloud planets. They are thought to orbit special types of super-strong neutron stars called magnetars. The intense magnetic field of the magnetar could potentially strip away the atmosphere of any planet close by, leaving behind a barren rocky world bathed in radiation. Mind blown, right? The universe is crazier than we ever thought, with more alien planets out there than sci-fi movies.